So hello everyone, I am Sai Venkatakrishnan, a PhD scholar from. Hello everyone, I am Sai Venkatakrishnan, PhD scholar from the Department of Computer Science and Engineering at IIT Madras. So I'll be conducting the live sessions for the course Introduction to Haskell Programming. So this is week one live session. So the slot for the week one live sessions will be weekly Friday 6 to 8 p.m. But due to some unforeseen circumstances, I had to reschedule my first week slot alone. So sorry for the inconvenience. So for this week alone, we are having it today on Monday. But from the coming week onwards, we will be having it on Fridays always, 6 to 8 p.m. Right. So this the live sessions. The main agenda for these live sessions would be one to mainly to clarify whatever doubts you have pertaining to that week or previous week lectures. So that's the main agenda for this uh, live sessions, right? So whatever doubt you have, right, however naive it is, feel free to post it in the forum or unmute yourself and you can ask the doubt and I'll try my best to answer all the doubts. Okay. So starting off, as anyone has any doubts in week one lecture so far?
Sir, could you please explain that currying concept?
Right, sure. Okay. The currying concept. Okay. Okay, so one is you want to explain currying concept, okay. Anyone else has any other doubt with respect to this currying concept? Or any other doubt? So I'll just jot down the doubts and I can look at the doubts and like sort of answer it in a particular way so that it makes more sense. So anyone else has any other doubts?
Sir, in the practice assignment of week 1, question number 3.
Okay, practice assignment week one. Okay, I haven't looked at the practice assignment. We will look at it. Cool. So practice assignment. Question 3 is it?
Yes, sir.
Okay, we will look at it. Right. Okay. Okay. So yeah,
I have one gentle doubt.
yeah.
Sir, actually, this Haskell programming, which industry is used or where it is used? Because I searched that Python and Java like that they are very popular, but why we are interested in Haskell programming?
Okay. Good. So let's first of all, I'll start with what's the advantage of Haskell programming, or why should we learn Haskell programming in the first place? So as everyone knows, right, Haskell programming comes under this broad programming style called as functional programming. Okay, so you all have heard of this term functional programming, I guess so, right?
Yes.
Right. So usually in the your first year of your computer science degree or anything, you probably would have started learning with C and or C or Python, and then you would have switched towards Java, C++, something like this. Okay. So C is sort of, it comes under the programming style called imperative programming, and Java and C++ are mainly object oriented. Excuse my handwriting, so it will be a bit clumsy sometimes, so sorry for that. Okay, so this is C and Java, C++, right? But there is this sort of programming style called functional programming, and examples of those include Haskell, OCaml, and other stuff. Like Haskell is like sort of like a main functional programming language, and even OCaml is also well known. Okay, so what's this functional programming language? What does it mean in the first place to become a functional programming language, right? So according to Wikipedia or any other site, right, function programming language is something where the constructs what you use, your main constructs that you use. So for example, in Java and C++, you always have a sort of like a class, and then you instantiate your class to form like objects and everything, all those like object oriented terminology, class, objects, inheritance, all those stuff come into the picture, and that's how your normal C++ program would look like, right? But in functional programming, everything is a function. Your basic constructs and everything, whatever you express, those are all functions, and everything would work on immutable values. So by functions, I mean they are pure functions. Okay, and it works on immutable values. That's the high level idea of function programming. So it's a way of programming using only pure functions and immutable values. So example of what a pure function is, what I mean by a pure function is, say I take for example a function, the sum function, right? Sum of a and b is equal to a plus b. So this is the function name, and I take two parameters a and b, and the result is I add these two values, and this is my result, the summation of two numbers a and b. Okay, so this is an example of a pure function. And what I mean by a pure function is whatever, or at like whatever time, so for example if I pass sum of 5 and 6, right, my answer will always be 11. It don't change to like something, say like at some specific time I invoke this sum with the same parameters 5 and 6, it returns 11. At some other time it will return back say 13 or something. That's not the case. Given these two parameters 5 and 6, my answer will always be 11. So given the input, if the input is same, my output will also be same, it won't vary, right? So this is what is a pure function. And another important characteristic of a pure function, important um, characteristic of a pure function is it does not rely on any hidden input, or does not manipulate any value. So for example, if I have say for example if I have say some global variable like glb equal to 0 or something, and now I say I have a function where like some function foo takes two parameters a and b, and what I do is I check the GLB value. If GLB equal to 0, then I return a plus b, or else I return a minus b. So this is some global variable, and since it's like a global variable, you can always manipulate this value. It can be anything. It can be 0 or it can be 1, based on it can be manipulated from any function, right? It has like, irrespective of whatever function calls, this can be manipulated. Okay, so now based on this global value, whatever I'm storing in this global variable, my output of this foo function varies, right? So say now if I give foo of 3 and 5, right, now if my global equal to 0, my output would be 8, or else it will be minus 2. Okay, or say like this is sort of, instead of having a global value, say I'm having some say it looks at the time. So instead of having like a global status, say it is looking at the current time. So if current time is say like if it's between 6 to 8 p.m. or something, it returns a plus b, else it returns a minus b, something like that. Okay, so then also your output changes based on what time it is being invoked. So now basically what happens is my inputs are same, but my outputs differ because of the if condition whatever I encoded in this function. And this if condition whatever I'm using, right, this specific condition over here, this current time, this condition is not being passed as a parameter to my function. So this is not being passed as a parameter. And what happens is, um, when you say so this is sort of like hidden. Okay, so say you're a new you're like new to the code base or something, like you're a new programmer, you're just looking at the function name foo of a comma b. Okay, it's just like sort of like it gives like sum of a b, something like that, some other function name, and you assume it to be like an addition operation or something. But internally, apart from using this two parameters a and b, it's using this current time also, which is not being passed as a parameter, but it is something given from the system itself, your operating system or something. You're using that current time as a hidden input into your function, which determines your final output. Okay, so this is an example of an impure function. So a pure function is something where your outputs are always deterministic. So a pure function is something where your outputs are always deterministic based on the input, and it doesn't manipulate any hidden input or something. Okay, so say for example, apart from doing this a plus b, say if I'm setting this um, say some other value, some other like say this globe equal to 0, right, like status variable or something, I can be setting this globe equal to globe plus 1 or globe equal to globe minus 1, something like this. So just looking at your function signature, right, over here, given it takes two arguments, it returns a value. You cannot reason out, or you cannot identify without looking into the source code of that function, that this function is manipulating a global variable which is not being passed as a parameter to the function. So this is what is, we mention it by like manipulating any hidden output input or some like a hidden variable or something. So this is usually like the terminology what they give to this is called as side effects. Okay, so of any function, the only effect of that function, the only um, the only thing that that function should do is it should take the parameters passed to it, it would do some computation or something and return back one output, return back a value. That's all a function should do. Apart from that, if it does some sort of, if it goes and manipulates any other global variable or any other environment setting or something like that, those are all called as side effects. Okay, so in a pure function, these side effects are usually not there. A pure function will be side effect free, and all its outputs would be deterministic based on the input, right? So in your max classes like 11th and 12th, right, usually your definition of a function is something be like f something like that, and you will have your like pre-image um, and your image or something like that, right? So a function say of so if you're sorry, so if you're writing an identity function, if you're writing like f of x equal to 2x or something, and this x is belonging, the range of x, this x, the domain of x belongs to all natural numbers, and this also belongs to all natural number, and the mapping is like sort of one to one. So given this x value, f of 1 means it will be 2, f of 2 means it will be 4. So it is 1 to 1, also it's deterministic, right? So here all it need not be like 1 to 1, but always it should be sort of deterministic, similar to how functions are treated in your maths subject. The same way in functional programming languages, the the programming style will always rely on these sort of pure functions working on immutable values. And by the term, what I mean by immutable value is, say for example in this sum function, right, this a specifically is a separate value, this b is a separate value, and this whole a plus b, this expression, is also a separate value. Finally it gets computed and that's a separate value, and none of these values are being changed. So this is sort of like computed or like created by the function, and these two values a and b, whatever is passed to the function, right, these are sort of immutable and this is not changed by the function. So after it returns back also, this a, whatever it had previously, say it had 5 and 6, right, a will still have 5 and 6, it won't be changed. So functional programming is mainly based on this, the concept is based on this programming style, which is um depends on this pure functions which act on immutable values. So now naturally the question what you will get is, okay, what's the big deal with this? What's the advantage of coding in this style using just pure functions and immutable values? There are many advantages. So one advantage is, say now if you are sure of having this pure functions, right, in a functional programming language, usually what happens is, say like if you provided you name your function name properly, something like logically it's well defined, say like something like this, and in Haskell you have this types, right, we'll discuss about types later. So say it has this type signature where it mentions it takes an integer, it takes two integers and it returns back an integer. Okay, so you all know what a sum is, and given this type signature, and given that Haskell at least till now always uses pure functions, it's a functional programming language, you can be 100% sure, or at least 99% sure, that it takes two integers and adds these two integers and that will be my output. And you can be sure of the fact that this sum function will be side effect free. That is, it don't manipulate any um, variable which is not being passed to it as an input, and it will not manipulate any other like global variable or something like that, and the output is purely dependent on whatever is passed to it as an input.
Sir, I
So
have one doubt here.
yeah,
So it is not affecting the global variable.
right,
If you're passing some variable like some a b,
right,
so I'm doing some manipulations on a, either a or b.
right.
I'm recursively pass it to again and again. So on that stage, it is side affecting that variables, that
Right,
parameters.
right. So that's a good question, Ganesh. So usually in Haskell, so in further week lectures, I will be looking into this most probably. So in Haskell, everything is treated as an immutable value.
Sir, I have one doubt. In Python, we have a list dictionary like mutable things. In
Right,
Haskell, we didn't have that data type.
right. Good question. Yeah, that's what I'm answering. So there are like mutable variations also in Haskell. So you have to sort of specify it using a different keyword, and usually in Haskell whatever the list or something, right, those are
Yeah.
all treated as immutable values. So
Okay.
sort of whenever you do recursive function using these lists or something, right, each time a new list is produced actually
Okay.
in the
Okay, sir.
memory. So that is a reason why like um, this recursive function and all those stuff you have to like properly code it, so that you don't just if you don't code it properly, right, then there's a high probability that there will be like you might run out of storage.
Yes, sir. Maximum recursive
Right.
depth is reached,
The
and
recursion acts on your stack space actually, so that you might lose control of. So that's what recursion and all the other optimizations, which we will cover in later lectures. So those come into picture actually, tail recursion and all those stuff. So we can discuss about it later.
yes, sir. In pure functions in Haskell, we can't use the global variable inside the function.
It is okay. I have not tried using a global variable but we can use it within the function. I have not tried it. I am not sure whether it throws an error also. But the general notion of a pure function is it should not rely on any global variable, or it should not um, uh, read or write from any variable apart from whatever is being passed to it as input.
Yes, sir.
So basically, what it as mentioned in lectures, your function should be sort of like a black box, and the only things what it should act on is the inputs, whatever is being passed to it. It should not go and manipulate, or it should not go and read anything sort of not explicitly being passed to it. You should not go and read. That's the whole notion of pure functions. And the advantage with respect to that is it becomes very easy for you to reason about what the function does. Okay, so now like when we tell pure functions, right, and by mentioning it as side effect free, and when we tell it just depends on your whatever input you are being passed, by just looking at the source code, whatever that function has, right, just the local scope, or just by looking at the type signature, you can have a pretty good idea of what the function does. Compare this to an impure function where you manipulate, or your logic depends on some global variables, or which are not being passed explicitly as inputs, right? The difficulty is now this global variable, what this does would be defined in some other part of your program or some other source code file. Now you should go and search over there and get that logical meaning, and in order to fully understand what a function does. So sort of having these pure functions helps you to sort of like have a sort of modular approach, and also it's being everything is being dealt locally, as in the parameters that are being passed, that's just whatever you are using, and everything is done, the computation, everything is just done locally. So the reasoning becomes very easy, and you need not go and search the whole code base to find out what a global variable does, and how the logic will change, how the outputs will differ. You need not have all those stuff. And the second thing is it is easier to write all the test cases, and it's also a lot easier to debug when you have these pure functions. So for example, if I take this function foo, which we had seen before, right? Say if it depends on this current time, and say the logic has so many if else conditions where between 6 to 6:30 your output will differ, between some other time your output will differ, something like that. It's all sort of like complex cases, means when you have to test your function in order to see whether all the corner cases are met, right, it becomes a whole lot difficult to debug, because it is highly probable that you might miss out on some cases, or some cases should not be triggered at all, and you might be in a position where you are not ready to encounter those outputs whatever the function is returning back, and it might result in some runtime error or something like that. Okay, whereas in a pure function it becomes a lot easier for you to debug, and usually you can do it automatically also. There are like tools, and it becomes a lot easier because everything is sort of localized, and it since it just depends on the input, right, you can do sort of like static analysis, or you can sort of the debugging becomes a lot more easier because it doesn't depend on all these global variables. So once your global variables come into picture, right, the disadvantage is, say um, your function foo is executing, and say if it's like a multi-threaded program or something, right? And this is in thread 1, and some other thread 2 or something, some other function say bar is executing, and if foo also accesses a global variable and bar also accesses the global variable, now there is sort of like a race condition, and the output whatever foo or bar returns depends on in which order this global variable is being accessed, right? Now you cannot be sure of what your output would be, both from foo as well as bar, and all this is sort of like tricky. But and also another so this makes debugging a lot difficult if you have impure functions. An important advantage of using these pure functions is you can easily parallelize it. Okay, so by parallelizing, as in like say if I have this two functions foo and bar, and if I just assume both are pure functions, means by pure functions I'm pretty sure that whatever foo does depends just only on its inputs, and whatever bar does depends only on inputs. So there's no way that there's sort of some like shared variable or like a global variable that's being accessed by both foo and bar. That is I'm sure of, since it's a pure function. Now I can confidently run foo on say a different core. So say you're having like a 4-core mission or something like that. Okay, and you can independently run foo on core 1 on a separate thread, and you can run bar on a separate thread, and both can simultaneously be executed without worrying about what your output is, because the output is always deterministic since these are all pure functions. So parallelizing the execution of pure functions is a lot easier. It's pretty straightforward compared to the previous case where we discussed this. If we are sharing a global variable, then this race condition occurs, and you should sort of like sequentialize which function executes first and which one then executes. So all this comes into picture. Whereas with pure functions, it's a lot easier to speeden up your application and parallelize it. That is one. So these are all the main advantages of pure functions. Okay, and also the final one is on the same lines of testing and debugging, right? It's easier to reason about and verify these pure functions. So verify as in, okay, I have this function foo and I'm telling I've written a code. The logic is it's doing some addition and some other computation, but you should have sort of like a mathematical proof or something like that to ensure that that's the case always. Sort of like you encode the proof or you verify that it always is the output, right? So reasoning about these pure functions is pretty straightforward, and this becomes a whole lot difficult when you switch over to impure functions. So these are all like the advantages of using this function programming style, having this pure functions and all those stuff. And that's a main reason why recursion is always sort of like important in these pure functions. So usually in C or C++, your basic programming construct you'd use to encode any logic would be sort of this for loop or a while loop, right? So for I equal to 0, I less than 10, I plus plus, and some logic you will be having some array access or something like that. And the problem with this is this for I equal to 0 or something, right? This sort of like your this sort of like mutable values. Okay, so you're updating this I value over the process of like executing the loop. And here recursion comes in handy, because in recursion usually you are calling a same function again and again, and all it sort of like works on all the immutable values, and the reasoning sort of becomes very straightforward, and owing to this notion of pure functions and all those stuff, right? Recursion is sort of like the way loops are being implemented in functional programming. So recursion is similar to loops because in recursion you are calling the functions again and again, and if it's a pure function, right, you are not changing any values, as in like you are not mutating any values, you are just working on these immutable values. Whereas in a loop, right, this iterator I whatever you are being updating throughout the execution of this loop, these are all should be treated as mutable values. And if we have to use this loop in a functional programming environment, it defeats the whole purpose of a pure function, because now your value becomes mutable. And in a pure function, the two main goals are it should be side effect free and it should work on only immutable values. That's the whole idea of the functional programming style, right? So that's why recursion is always a main uh, programming construct in this line of functional programming. Okay, so hope this answers the query, like why Haskell is important or what are the advantages of using a functional programming style. Any query still now, whatever I have explained?
No, sir. Clear, sir.
Okay, cool. So Haskell as such is, I'm not sure of the industrial use cases, but it's being used in uh, Facebook and other companies. So for example, my background is in OCaml, but I'm sort of know Haskell also. So OCaml, for example, is used in Jane Street, right? That's a functional programming language. OCaml, it's pretty similar to Haskell. So it's being used in Jane Street, Facebook, and lot of other companies, like a search engine company called Ahrefs. So these are all the companies that are using OCaml in their day-to-day tasks, day-to-day programming tasks. So for example, Jane Street, it's not like much heard of company in the likes of Google or Microsoft, but sort of like it's a highly established company. It is a fintech company, and the their day-to-day use cases involves writing code which their code base interacts with these stock exchanges. So they call this as like high frequency trading, right? And the code usually has to be at executing at high speed, right? There should be no drop in latency or anything, and they are consistently using OCaml. So they had this just an anecdote. So back in 2004 or something, their code base was mainly in C, C++, all those stuff, and they wanted to shift their code base to some other language like Java, and they tried for like 3 to 4 months, I guess, in to shift their code base to Java, and it was pretty difficult to shift to Java. And what they did is they tried OCaml, which is a functional programming language. And to their wonder, what happened is within 6 months they were able to successfully transform all their most of their code base to OCaml, shift everything to OCaml, almost all their code base to OCaml except a few performance oriented modules, we can say. So most of it was shifted to OCaml, and still now like they are sort of like the main users of this OCaml functional programming language, and they are contributing much also. So this sort of like uh, it's a good example where like usually like people who tell a functional programming language are pretty slow when compared to imperative programming language like C and all those stuff. But if you take the example of this company Jane Street. Their day-to-day task involves this high-frequency trading, and they cannot compromise on the latency or the code execution speed or the performance aspects, because from that's what like determines whether they gain a profit from the trading in the stock exchanges or not. And they are successfully using a functional programming language, and this is, and it becomes, and they have also mentioned it becomes a lot easier for them to test and debug this production code, and they face a lot uh, uh, less errors compared to when they were in C or C++, right? So these are all the advantages of functional programming language. I just saw someone raised their hand. I guess Danyashri or someone else.
Yes, sir, it's me.
Yeah.
Sir, could you suggest any good book for Haskell, sir?
Okay.
Is there any book for Haskell, or could you suggest any good book?
I guess this was answered in the forum in one question, I guess, on the NPTEL forum for Haskell. The TA has mentioned around like 3 books or something like that.
Okay, sir, thank you.
Right. So for whatever I am presenting, or like how I'm learning Haskell is, I'm just looking at the video lectures, and I'm any plugin gaps. So like since I know OCaml, the conceptually it's pretty similar, but it's good to follow a book. So I guess they have mentioned 3 books. You can just have a look at those 3 books and see whichever is comfortable to your taste and all those things, your which suits you best, and you can follow that specific book. And usually like sort of the basics of um, Haskell would be pretty easy, but the main difficulty is like when you go into the advanced topics like the type system and all those stuff, right? It's important that you um, have like a nice book that would be really helpful, I guess. I guess Ganesh had suggested one book, right? Yeah. So these are all the 3 books, Danishri, that they had mentioned in the NPTEL forum. Learn New Haskell for Great Programming in Haskell and Thinking Functionally with Haskell. So you can either like stick to one book, but I suggest you do not follow that like a single book cloud, because sometimes like the case is in some books some particular chapters are very well written, and in other books the other chapters would be like explained very well, right? Like some books would be like sort of oriented mainly to the advanced audience, so their advanced chapters like the advanced type study and all those stuff would be explained very well, but whereas the basic chapters would be sort of like sparsely explained, and they won't go into much detail. Some books they would explain all the basic chapters very well, and the advanced topics they would just go through very fast, and they won't have any much of like examples or all those stuff. So I suggest it's better you like sort of um, refer to all these 3 books, as in like just have a quick glance over the contents, right? And whichever you find more examples pertaining to that chapter or something, you can follow that book. I guess that's the best way to learn any programming language.
Yes, sir, thank you.
Okay, cool. So now coming to the concept of currying, right, which Ganesh had asked. Okay. So the concept of currying is sort of like is so basically Haskell, right? It the concept of currying is, say you have a function um, say it takes function foo, it takes like three arguments a, b, c, and d, right? And usually the way how so coming just giving sort of like a background, okay? So it is not. Um, so there's something called as lambda calculus. So this is like off topic. So lambda calculus is nothing but a set of like three terms, okay? Uh, it's like a minimal set of three terms. So like how in if you take your any programming language, you will have sort of like functions and then all these operators plus minus all those stuff, then the numbers 2 3 4, the values like the constants and functions, and then the notion of class or something, all those stuffs are there, right? Lambda calculus is sort of minimalistic minimalistic programming language and contains just like three terms. So one term is called as a function, which is called as known as the lambda term. So lambda x dot y, something like this. And the second is just a value, sort of like a constant. We can just term it as b. So just a value. So these are all like constants. Okay. And the third is a application. Say this application is usually of the form a lambda term followed by so this is usually like of the form uh, term term. So basically a combination of two terms. Okay. So this is what a lambda calculus is. Okay. It is just like sort of a background I'm giving. So in this lambda calculus, this this is called as a lambda term. And this lambda term is the one that, so usually in your right. So this lambda term is what in Haskell you are seeing those as functions. Okay. So let me just change this. So in a lambda term, when I say lambda x dot x, it is nothing but you are writing a function foo. It takes a parameter x, and what it returns back, what's the body of the function? This is the body of the function x. Okay. So this is what is there in this lambda term is what is represented in Haskell like this. And by the term value or constants, it can be anything as in like integers or floating point numbers or a string like Haskell, right? Something like this. Okay. And this application which consists of two terms. Okay. So here by a term, it can either be a lambda term or a value. So by an application, it can be sort of like lambda x dot x, okay, followed by say I am this term. So this is sort of a value. So value is also a term, and this is also a term. Specifically, this is a lambda term, and this is the third case. So this is called as application. Okay, and what happens is in Haskell, this is represented as foo of 5. Okay, so this is the function foo, what I am representing over here, and this 5 is same as this. And foo of 5 in Haskell, what happens when you sort of execute this? It passes this 5 to x, okay, and it returns back x itself. So the answer is 5. So this is what this function application. So the way Haskell is designed, right, or what's the basic of Haskell? This is what is the basics of Haskell, lambda calculus. So the Haskell programming language is sort of like a practical implementation of a language called as the lambda calculus, which consists of just these three terms. Say if now you want to write a program which sort of finds the shortest path between two vertices on a graph, using Dijkstra's shortest routing algorithm or something, you can use these three terms alone of lambda calculus and write a big program. It will be too much of complex cases and all those stuff. It won't be easily readable, but it is a Turing complete language, and just using these three terms, you can write any logic, right? But in real world scenario, this won't be useful. You cannot easily code using this language called as the lambda calculus. So Haskell comes into a picture, and Haskell is sort of like a practical implementation or a practical design for this language of lambda calculus. So this is what is the background what I want to give. So why am I explaining this? That would be your natural question. So why I explain this is the concept of a function, right, in Haskell is that it is of this form called as the lambda term, sorry, right? So the concept of function in Haskell depends on this lambda term, which whose meaning it derives from this language called as the lambda calculus. So just by seeing this term calculus as like, you need not like worry, it's like sort of like fully maths or something, nothing sort of that. Since all these terms were discovered in the late 1940s and all those in those time period, and usually the ones who coined these terms were mathematicians turned computer theorists, and they sort of like had this fantasy for mathematical terms, right? So they called that language as lambda calculus. There's nothing more to it. It's just like sort of like rules, right? Your any programming language is sort of set of rules, and it basically derives from maths only. So okay, so this is the basic programming language, and Haskell sort of implements this programming language, and any function in Haskell is what is linked to what is known as the lambda term in the lambda term in the lambda calculus. So if you look at what a lambda term is, it's of this form: lambda x dot the body of the function. So this x is something, the parameter, okay, and the body of the function is whatever logic you encode into. Now I've mentioned that in Haskell the function whatever you have is the lambda term denoted in the lambda calculus. Now the next question is, okay, in Haskell we have this say sum of a and b, right? It has like two parameters, but here the lambda term just has one parameter. Now what's the how is this possible in Haskell when it's not possible in lambda calculus? So in lambda calculus, when you mention like two parameters, right? How it is defined is, say, lambda x dot lambda y dot x plus y. Okay, so basically what happens is, this is an interior function and this is the outer function. Okay, in a lambda calculus, the basic idea is any function, any lambda term will only have one parameter. So as mentioned over here, in a lambda calculus we have three terms, right? So the term, any lambda term, it will be of lambda x dot whatever is present inside the body of the code. Okay, and in this body it can be another function, can be a set of values, any logic, anything it can be. Okay, so in a lambda term it's always like one parameter and the remaining is the body. So now if you want to express sort of like a 2-argument function, right? This is the way we express a 2-argument function. Sort of like the outer function takes 1 argument, and then it passes on the argument, it returns back what is this the body of the function, where it sort of like how this will be used, say like lambda x dot y x plus y. How this will be used is, say if I pass 5 and 6, these two values I'm passing to this function, okay? How this is being executed is as follows. First, what it will do is it will pass 5 to this x. So this is the first function, and the function takes one parameter which is called as x, and then what it returns back is this part over here, this lambda y dot x plus y. But before returning, what it will do is, wherever this x is present, right, it will replace that with 5. So the thing, what the output of this function, outer function, when I pass 5 to it, is as follows: lambda y dot 5 plus y. And now 6 is still remaining, and when I pass 6 to y, the y would be replaced by 6, so it will become 5 plus 6, the answer is 11. So this is how in lambda calculus a 2-argument function or anything is encoded. Now in Haskell also, it's exactly the same way how they treat a multi-argument function, 2 or more arguments. So that's why in the lectures, if you read this, they explain the fact that if you have a function foo of x1, x2, x3 up till xn, right? It's nothing but foo takes only one function, one parameter x1, and it returns back a function having all these things, a dummy function sort of f, which sort of takes x2, x3 up till xn. It's sort of like, for example, how can I do this? Okay, instead of going till xn, so say this is your Haskell function programming thing, right? So assume all this to be integers, x1, x2 and x3, and it returns an integer. So how your type signature would be is as follows: it takes 3 arguments, int, 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 and it returns back an int. And how this is encoded, or how this is treated in Haskell, right, based on how the understanding of our lambda calculus is, it will take a single argument and it returns back this whole function. And this whole function, what it does, here again it will take a single argument and it returns back this whole function. So it's basically lambda x, x1, lambda x2, lambda x3, and followed by whatever is the body. And this is a function 1, this is an inner function 2, and this is inner function 3. And how an execution happens in Haskell is, you pass the first parameter, whatever you are passing, it first gets the x1, all the x1s get replaced to that specific value, and the output is a function itself. And in that function you will pass x2, and all the x2 gets replaced, and now you get a third function, this function, where x3 is applied to this int, and finally you get an int value alone, right? And this concept as a whole is called as currying. So the whole concept of currying is, if you have a multi-argument function like x1, x2 and x3, it is just a syntactic sugar, or it's just a way of like an easy way for you to express the logic in Haskell, where it gives you the easy notation of assuming all these three are being passed as three parameters or three arguments to the function at the same time. But internally, how Haskell treats this foo function is, it treats this as like three sets of functions, where the output of the first function would be a function which gets two integers, and output of applying x2 would be a function uh, which gets x3 alone, right? So you can ask, okay, what's the big deal with this? What's the advantage of using currying and all those stuff? For example, say you have a function sum of a b equal to a plus b. You have this function, and in your program logic, you are pretty sure that one argument to this sum function is always 5. You are pretty sure. So in that case, what you can do is, you can write a new function sum5 equal to sum of 5, and the output, okay, would be a function foo. So here the type signature of sum would be int. It takes two integers and returns back an integer, right? Now this, let me give a name, sum5. Okay, so this is the function name. Okay, and the type of this sum5, so when I apply this 5 to this sum function, it returns back a function which is associated with this sum5 name, and the signature of that function would be as follows: int followed by int. So it's basically this part. And now if I apply any value like sum5 of 11, my answer would be 11 plus 5, 16. If I apply sum5 of 12, my answer would be 17. So this is what is the advantage of currying, and this is called as partial application. So in some logic or some programming logic, sort of like you don't want um, phi to be always passed explicitly. You just want to be encoded as part of the logic or something like that. So you can sort of define this generic function sum, and you can derive a specific function where one of the operands is phi, and just the other operands would be passed to it, right? So this is an example of currying, and this application, this technique is called as partial application, where you're sort of like you get a partial function by applying just passing one para argument alone, and that partial function you are now using it in the other places. So this is the concept of currying, and the um, the reason why Haskell followed this concept of currying would make much more sense if you understand this lambda calculus, which is the core fundamental idea of Haskell, uh, on top of which this Haskell language and almost all functional programming languages are designed, right? So any doubts in this currying?
No, sir. Clear, sir.
Okay, cool. Anyone else, any doubts in currying? Okay, cool. So this is Kali, and so what I can do is I can share my terminal and we can just work through a couple of code or whatever I showed in this currying example. We can see whether it works out in the Haskell code practically. Okay, so let me share my other screen. Um, Entire screen. So is my screen visible?
Yes, sir.
Right. So so I assume most of you have installed Haskell in your systems.
Yes,
Is
sir.
anyone facing any trouble? I guess the installation instructions are pretty straightforward. Um, so if any one of you are facing trouble, you can most probably try googling it. Or if you are still not able to solve any solution, feel free to post it on the forum. We will look into it. Uh, if sort of like you don't want to go through all this um, hassle of installing the dependencies and all those stuff, you can sort of try looking into a Docker container which has Haskell pre-installed as part of the container. Okay. So now assuming like everyone has installed Haskell, right? So we are using this interpreter called GHCI. So it is similar to your Python interpreter. So usually Haskell is sort of like a compiled language, but for the time being, we will be using this interpreter for like fast coding and like looking at the output, right? So when you start this GHCI, right? When you start the interpreter, you get the version number. Currently, it's my version number is 8.6, and you get this key term called as prelude. So this prelude is nothing but sort of like a standard library which contains most of the functions that you'd be requiring for your day-to-day tasks when you use Haskell. All the AND operation, the summation, uh, arithmetic functions and all those stuff, everything, your display functions and everything, all those would be part of this Prelude library. So this sort of like a standard library, which is always linked in, always like loaded when you start up your interpreter. So that's what this Prelude is all about. So now, say if uh, so I have this source code over here. So here, so all these are sort of like examples from the the lecture slides only. So I'm sticking to those examples, but I'll be touching upon a few extra things also. So one is this XOR bool, and all these things, right? So this is one function which performs takes two boolean variables and returns back the XOR of those two boolean variables. Okay. So so I'm using this. So anything starting with a colon sign is sort of like a special command to the interpreter. So here I want to load a file into the interpreter. So this is sort of load source.hs. So I'm loading whatever is present in this file into my interpreter. And if you notice over here, by default, um, it is whatever I've coded in this file, right? So the source.hs Haskell extension it's part of your main module, and when you load this source file, it's basically loading that main module, whatever functions are there, it's loading it. And here the prompt changes from prelude to main. Okay, if you notice, so it's just a notation where it denotes that now your main module, whatever you have loaded, is active. So now if you sort of use this XOR function,
Sir,
yes,
so it will change to prelude to main, right?
yes,
So in prelude we have some helpful functions for our day-to-day life.
right.
If we change it to the main file, so can I ask that default function in that main folder?
Yeah, it will still be uh, available. One second. And to pretty much.
So I think it's true and false.
Wait. Right. So for example, this is a function and, which is sort of, we are getting it from the standard library. I have not defined this and function. Okay, and this is still active. Okay, and for example, your plus operation 222 plus 5. So this plus is also defined in your prelude library,
Prelude later. Yes, sir.
right? So the prelude would be still active unless you don't define a function with the same name within your main module. Till then it's okay, right?
Yes, sir.
So okay, so now going back to the things, right? So I did XOR of true and false, it becomes true. So either one should be true, that's what XOR is, or both should be false, something like that, right? So this is XOR and takes two Boolean arguments and returns a Boolean output. Now to see what the type of my function is, the function type, I'll be using this interpreter command colon type, similar to how we used colon load. I'll be using this colon type followed by the function name. It returns the function type. So I assume in most of your assignment questions, you would be asked to find this function type and all those stuff. So I suggest you first try to do it by yourself. Try to find out the function type by looking at the question, by looking at the logic, and try to get the nearest, the closest correct answer possible. And then you can verify it by looking at the output of the interpreter. Why I'm asking you first to do it by hand, by yourself, is usually in your NPTEL exams, you won't have this interpreter assisting you. It's just you and just the MCQ questions. So at that time, you should not be reliant on your interpreter. So you should sort of understand how to find out or how to write out these function types by yourself. Okay. So this arrow mark over here denotes a function basically. It's used in a function type. So by here, by looking at this function type, you can see that it takes like two Boolean arguments, and returns a Boolean argument. So this is like sort of the easy way of looking, but the actual way, taking this concept of currying into picture, it's sort of like takes one Boolean argument and returns a function which has this particular signature. So for example, let me add another function, sort of like XOR t equal XOR t of uh, equal to XOR of 2. Okay, so I have assigned this XOR of t. So it's nothing but XOR of true I have given. So let us look at what the type of this XOR of t is. So if you notice, it is not this free boolean. It doesn't take two boolean arguments and returns a bool. Instead, you notice the type of this function x or t is now it just takes one boolean argument and returns just a boolean argument. The reason being, as we had seen in the explanation before, the first argument is hard coded to this value true. So now it just depends on what your second argument is. So that's what it denotes by this second boolean argument, and the output is a boolean value. So now if you give XOR t of false, it gives true, and now if you give XOR t of true, it gives false. So I can repeat this for say like if I want to have say for example sum of three integers, right?
Sir, could you explain that previous example because I can't clearly understand that one?
This one is it,
Yes, sir.
right? So here what I have done is, usually when I have to use XOR function, it expects two arguments,
Yes, sir.
right? But here over here, XOR t of this over here, let me. So over here, I am just passing one argument true
To that XR function.
to the XOR function. This executes properly.
Yes,
The
but that
reason,
XR function, it's take two argument, right? But you are passing that only one argument. So how it will that another argument?
exactly. So this is where the concept of currying comes into picture. Here the XOR function, the easy way of seeing what an XOR function does is it takes two arguments. But internally in Haskell, it depends on, it encodes whatever this lambda calculus does. And in lambda calculus or in Haskell, every function just takes one argument. That's it.
Yes, sir.
Okay. So now if we see this, if we have the understanding that every function takes one argument alone, you will notice this. This is the first argument bool, and the output is this whole thing, bool arrow bool. And what this denotes another function actually, which takes an argument, just a single argument bool, and returns a boolean argument, a boolean value. So this is
Yes.
what is being encoded over here, XOR t equal to XOR of true, where I am passing just a single argument, and my output is this whole function, which takes just a single argument bool and returns back another bool. So over here actually it returns back a function in the first place, and I pass a single argument, and that function is having this type signature. So now if I use the command type followed by XOR of t, you notice over here this is the type signature and not this.
Yes, sir.
So this is what currying is all about. So the way we look at a multi-argument function is just sort of a syntactic sugar, where just for the ease of programming, we mentioned that it is taking two arguments and returning back a boolean value. But internally, this XOR function just takes a single argument and it returns back these two this function having this specific type signature. And the second argument is then applied to the function with whatever is being returned, and finally your output comes. All this takes place internally actually when you pass the two arguments. Say now if I pass XOR true false, right, the way this gets executed is first true is being passed, okay,
Yes, sir.
and what happens is in this logic over here, b1 and then not b2, right, wherever b1 is present,
It
it
will
is
the
replaced by
true
true
value.
actually.
Yeah.
And now you apply false again. To what do you apply false? This whole thing is actually treated as a separate function.
That is
Say,
XR.
say it's sort of like treated as an anonymous function because everything is done internally. You don't name it with an explicit name unless you have a assignment statement like this, right? this anonymous function will have a logic like this, where instead of b1 everything is replaced by true, which is the first argument, and to this anonymous function you are now passing the second argument false, and now b2 is replaced with this false. Okay,
Yes, sir. Clear, sir.
right. So this is what happens in currying. So the key concept of currying is becomes pretty easy to understand when you convince yourself that in Haskell every function takes one argument and it returns back a function, and that's why in Haskell functions are treated as first class values. Okay, sorry, I shouldn't have done that. So functions are treated as first class values. What I mean by this statement first class values is in a C programming language or any other in C or C++, you don't you what all can be passed as arguments to a function. You can pass an integer, an array, a structure, string, floating point numbers, or any other values. But you won't be passing a function as such. You will be passing something called as a function pointer, but that is different. Okay, you are just passing something called as all the values. Okay, integers, strings, and all those things. You won't be passing a function as such in a C programming language. So for example, if you have two functions, you won't be passing one function, that name of that function as it is, to another function as an argument. So in those languages, we mentioned that functions are treated as second class citizens, as in they have sort of like a limited value. They can just be invoked in a call statement. They can be like called, that function can be called and parameters, arguments can be passed to it. But that function itself cannot be passed as an argument to another function. Whereas in Haskell, you can pass functions as arguments, or it can be returned as values as an output from a function. So that's why we mentioned functions are treated as first class values in a functional programming language like Haskell or OCaml. The example over here is this concept of currying, right? Because here you are actually creating a new function. What's a new function? You just pass a single argument through to this XOR function, and the output is actually a function. You're returning, your output is a function itself. You're not returning a Boolean value or an integer value, you're returning a function itself. So that's why functions are treated as first class values in Haskell. Okay. So any doubts in this concept of currying or looking at this type signature and all those stuff?
Sir, I have a doubt in comparison operators, sir.
Right.
So I
Okay.
compare that 4.1 is greater than 4, it throws an error. So it makes this. But when I'm using this, like it says that you can't compare different data types into a single operator. Like you can't compare a floating point and integer, and you can compare two different data types within this comparison operators.
Okay, so did you assign it something like 4.1 and 4, or as in like did you assign it as part of some variable name? Did you associate that constant to? Did you store it in a variable and then compare it?
No, sir. I just written a like I think I written a function like comparison A B equal to A greater than B.
Okay,
So I just passing that parameter. So something like that I doing. but it shows like no, it is not.
So
Its
say
type is
I
error.
compare two int and then it returns.
No, sir. Float and int.
Okay, float and int it don't work. I guess.
So because I'm passing 4.1 is a float number, right? But how we say it is an integer?
Okay, so so float and integer int is actually two different
Data
types,
types. Yeah.
data types. So you cannot mix two different data types. And in Haskell, everything is sort of like a strongly typed system, and everything is done at static compile time itself. And it's not usually allowed. So here actually, when I'm doing 4.1 and 4, right, I assume that the interpreter is assuming this 4 to be a floating point number. So
Okay.
because
So the
usually floating point is subset of, sorry, superset of whatever integers, right?
yes.
So it treats this 4 also as a floating point, and it's okay for that. But when I specifically mention one as a floating point and other as an integer, it won't work.
Okay, sir.
And it is usually the case that that's actually safety mechanism, because like there are like tons of issues like security issues when you mix floating point and integers, these rounding up and rounding down operations, especially in computations where we require precision and all those stuff, right? It is better if we specify whether we want a floating point or an integer. That's the sort of like that's a hassle with this sort of type systems, because you have to specify a float or an integer and you should stick with that. But the benefit that you get is your code becomes a much more safer from all these runtime errors that might pop up during execution.
Yes, sir.
Okay, and another aspect with these operators, for example, 2 plus 3, if I write over here, this operator is also actually a function. Okay, but I'm treating this as an operator. So basically, for example, if I want to invoke a function, this XOR of true and false, okay, uh, this is my function name and I'm passing two arguments. So this no this type of passing invoking a function, right, this is known as the prefix notation. So prefix notation, as in I have this function name at the starting itself, the prefix followed by the argument true and false. This over here 2 plus 3, this plus is actually a function. You name this as an operator. An operator is nothing but infix functions in Haskell. Infix, as in, is a way of invoking this function. It's the way how a parameter is passed to this function, right? So infix, as in, you don't have like plus followed by 2 and 3. Instead, you have 2 plus 3, right? This plus is in between. This style of invoking a function is known as the infix notation, and usually any um, invoking using this infix function is called as an operator. Okay, so for
Yes, sir.
example, if I want to have the same XOR of true and false to be invoked using an infix style, right, I can use true backtick. Let's see, it works. So over here, so this is sort of the prefix file, prefix notation, and this is an infix notation. So here a prefix notation, as in I have the function name at the start and then I pass the parameters. Infix notation is somewhere where I place the operator or that function name in between, and on either side is the parameters. And how I transformed this function name XOR into an operator that is to be invoked in an infix style. Sorry, is I added this backtick uh, symbol before and after the function name. So any function name, right? For example, um, sum of 1 and 2. Okay, sum is not defined, and C of false and true. So and C is like a custom function which I have defined in my source file, which does an AND operation. So and C can be also transformed into a infix form where I can do like this. Okay, this is just the same logic, the same function is being invoked, but just a way of invoking. So this is the prefix style and this is the infix style.
So every prefix style notation can be converted into infix notation, sir.
Okay, so um, I guess yes. I'm not very sure of that. Um, I mostly yes. It can be changed to an infix notation.
Yes, sir, but infix notation may or may not be changing to the prefix notation because is that work for 2 plus 3 is fine, but plus 2, 3 is work or
So a good question. So for plus 2 and 3, right?
yes,
This
sir.
is the notion. So
Okay.
this is the function name actually within parenthesis plus 2 and 3. So actually, if I give the command type followed by the function name, it gives me the function signature. And in the same way, if I try to give for plus, right, it won't give. But if I give it like this is the function name for the operator plus within the parenthesis. Now if I give, it gives the function signature.
Yes, sir.
Okay, and so this is what. So similar way, for example, I can give for into also multiplication. I can give for the exponential sign, right? So all these can be treated as functions the same way. So basically, the point that I want to put forth is the operators that you have been using 2 plus 3 or 2 divided by 5, 2 into 5, anything, right? All those infix operators are basically functions. They are defined as functions, part of your standard library. Okay. And another command that you want to get used to in this GHCI is this info command. So for example, if I pass this info command on this custom function and C or say the XOR function, it returns back some information similar to what we got when we use the type command. And also in addition, it also defines the location in the source file where it is being defined at line number 2 or line number 12. So for example, XOR is defined at line number 2 and AND is defined at line number 12. Is it? So I had changed this file, so it's different.
Yes, sir.
So this is one. And now if I use the same info command to a operator, for example, into. So here it becomes a pretty interesting. So for now, for the current lecture, we'll ignore this part over here. So this is something it's dealing with polymorphic types. Let's ignore this part. We will look at this last line over here. Infix L 7 star. Okay. So this let's look at one by one. What does infix L denote? Infix L is nothing but it denotes it's being used as an infix operator, infix notation, and this L over here is left associativity. Okay, that is one, and followed by that this number 7. This number 7 is nothing but precedence. So precedence is usually like your board mass rule, division and multiplication is higher precedence compared to subtraction and addition. So in the same way, all your operators, your um, any operators that you are using. So for example, this notation over here, right? This is also an infix operator. This sort of like function application. So the precedence is usually 0 to 9, and higher the number, higher the precedence. Okay. And finally, this star symbol over here denotes the infix operator, what you'll be using. So 2 into 3. So that is how you'll be denoting your infix operator. So this is what your the information that you get when you pass this info command and the asterisk operator. So you get, it's like left associativity, precedence is 7, and this is the infix operator.
Sir, what is the meaning of that left associativity?
Right, good question. So for example, if I pass 2 into 3 into 4, okay, the answer is 24. How this is calculated is, so 2 into 3 is first,
Then,
and then it is 4. So basically multiplication is commutative, so you won't find any difference if you follow a right associativity or left associativity. But let's look at an example where it makes a difference. So for example, let's look at the exponential. Okay, so
yes.
so this is, it mentions infix r. So
So right
an infix
associativity.
operation, right associativity, and the
Precedence.
precedence is 8, and this is the symbol for the infix. Okay, so now I pass 2, 3, and 4. The answer is this
Yes,
huge
sir.
number. Now, for time being, let's assume it's left associative. So what happens now? First I do 2 power 3, and then I do 2, that answer I do
So
the
it's
power 4.
different from the previous
So
one.
it gets 4096. So it's not left associate. So now if I change the brackets, let me start fresh.
So that means left associativity means it goes from left to right, and right associative means it goes through right to left.
Something like that, yeah. So
Okay,
this
sir.
is how the pairing occurs. So this is how the execution occurs.
Yes, sir.
So now this is right associativity. So in a similar way, now let's see some other info of how about this. So this over here. So just so even I'm not sure what all these things denote. Okay. So just look at this second line over here. Okay. So this is the function notation. So for example, if I give type of XOR, so this is what you get, the type signature, and this is the application sign, this arrow sign, and this arrow sign is actually in between, right? This sort of like an infix style. So this sort of like an operator, and when I use the info command, it shows it's right associativity. Infix are right associativity. So by right associativity, it's nothing but the same way, right? Um, so as we had done previously, this 2 and 3, 4 this way. So not in this way, but this
Yes.
way we should do right associativity means. So in the same way, I should add brackets like this. Okay.
Yes, sir.
So now it makes now you can clearly see how this currying concept. Okay,
Yes, sir.
so you are seeing this as sort of like two arguments, but this notation present over here, the application operator, it is right associativity. So it takes one argument and returns a function having this signature. So this is how it works. So in the same way, if I have say now 3 bool values or something like that, right? So first it will do this, and then this, and finally this. So this is right association. So it takes one argument and returns back this whole function. and this whole function is where it takes another boolean argument and returns back this whole function. And finally, this function will take just one boolean argument and returns back this boolean argument. So this is how the concept of currying is. For syntactic sugar, we just look at this as it takes three boolean arguments and returns back one boolean argument. But the concept of currying, which is fundamental to Haskell, is it treats these functions as first class values, and this is how like it's treated. And this is the reason why this operator over here, we mention it as right associativity.
Yes, sir.
Okay. So
Sir, could you please bit explain that guards concept, like some A B, that vertical bar indentation between A?
which one?
I think it's
Oh,
third
in
lecture.
the source code.
Haha, that line number 10, level 12. Yes, sir. So if
Okay.
it's like if condition or
Yeah. So this is sort of. So in Haskell, we mentioned this as pattern matching. Okay.
yes,
So
pattern.
similar to how you do switch case in C, right? So switch case in C is sort of like not like sort of honest comparison, because pattern matching is sort of more powerful in Haskell. Okay. So a switch case in C is like you pass some integer, like you have like case 1, case 2, and then a default case.
Yes, sir.
So in the same way in Haskell, this is how function sorry, pattern matching works. And in Haskell pattern matching, okay, so this notation is nothing but this is case 1, case 2, and case 3. This is just to denote different cases.
Okay,
So
sir.
in a C statement, you have this break command, those stuff, right? So in Haskell, this is the way you denote this different cases. And in Haskell, this pattern matching is sort of like more powerful, because you can pass a list or you can pass any type, right? And you can sort of like have these are called as guard conditions. So once this condition is fulfilled, your execution enters into the body and it returns back. And similar to how your switch cases work in C, right? The order in which you denote these um, the order in which you encode these cases, right? Some can be overlapping. So for example, I can have another case like n less than 1. So say for example -2 I am passing, it is applicable to both this case as well as the second case. So it depends on which one is written first, that will be executed first. And this otherwise is sort of like a keyword which is acts as a default case. And in Haskell, since it's strongly typed, okay, and you know that it is sort of like, for example, so in some cases, right, when you don't have some cases, you don't specify some cases, usually the compiler will throw out an error stating that the pattern, like a warning or something, where it mentions the pattern matching is not exhaustive. So for example, let's look at this itself. So n less than 0, n less than 1. So let me comment out this and see what happens. So just a bit of thing. So if now it's in the current main module, if I want to use a different source file, I should use this command :m. This sort of unloads the current module. So now you can load any other file. So here I'm loading the same file again. Parse error on input. this. Okay,
Sir, I think that error is factorial and that colon, sir.
oh, sorry. Okay, thanks. So,
Oh no. No. I think you are putting equal to sign
okay,
instead of that colon.
let me just. Okay, that shouldn't be an equal to actually. It's just the equal to is right. So now if I just comment out this part, it doesn't show any warning. But usually the case is right. In some cases, usually you will come across a case where, um, for example,
If it does not match any pattern, then it will throw an error, sir. Like pattern
right.
is not
No,
matching.
so if your matching is not exhaustive, right? For example, factorial of 1 if I pass over here, right?
Yes,
Non-exhaustive
sir.
pattern. So it is sort of like a runtime error. Actually, it throws an exception. But in most of the some cases, statically also it can determine, right? Since you know it's an integer, or like say for example, in later lectures, you will be coming across some types and all those other stuff. So, for example, if you consider
Sir, before going to that one, that Guardian we are checking, sir,
right,
seventh line and eighth line. So we have a multiple overlapping statements. So my doubt is if Haskell saying that if for example if n is less than zero, then n is less than minus one, minus two, something like that I wrote. So if that thread is going one by one, so it is seeing that first guard, and that is true. So
right.
it will go to that body. So is it going forward? That means is it going further and read all
No,
the
it is
guards
a
are
break
coming to the
statement
first one?
actually.
Huh.
So only
Okay.
one guard condition will be evaluated. So by default, there is a break statement.
Okay. So there is no if it's coming to this body, then it's going. It does not going to
It
check on
oh
any other
no,
thing.
that's like first come first. So that's it. It doesn't enter into any other guard condition once it enters body of the guard condition.
Okay, sir.
Right.
Because
So
in that lecture I think professor says that it goes through the every guard, and which guard is come in first place, so it will go to that one, so that's
right,
why
right,
I'm
yeah,
asking.
yeah. So the first guard it gets satisfied. The answer is true. It goes into that guard condition. So
Okay,
for
so my
example,
specific, yes sir, my specific doubt is if three guards are executed, like three guards are overlapping.
right. So here, for example, I give factorial of 3 is greater than 1, greater than 2 also.
Yeah, yeah.
So it will execute the first one only. Sorry, the second one. Uh, it it will check the first one, it's false. It will check the second one, true. Happily, it goes and executes. It won't go and check n greater than 2.
Okay, okay, sir.
Okay, and in this you will later come across some types or other types. Okay, so basically what happens is integers is nothing but all from minus infinity to plus infinity. Okay, so it has a specific range. Whereas boolean value, you just have a true or false. Okay, now if I pattern match anything, so instead of this passing of to factorial, if I pass a boolean value, and if I'm just looking for this variable true, right, and if I'm not looking for false, I guess most probably Haskell will throw an error saying that the pattern match is not exhaustive, because it knows for sure that a boolean value will have only two values possible, true or false. For the true condition, you have given a body, the execution logic, but for the false condition, you have not mentioned anything what will be executed. So that's sort of like a runtime error it will result in when you pass a false argument. So these things, I guess, Haskell will statically find out and return a warning or some compile time error while trying to compile the source code. So we can have a look at it when we are going through type systems in detail.
Yes.
So these are all the topics I wanted to discuss with you all in today's lecture. Hope you understood the concepts, and it's 8 o'clock now, so I should wrap up the session. Any other queries you have, specific queries or anything?
Sir, I asked a doubt from the practice
Oh,
assignment.
okay, sorry. Let me, can, week one practice. Okay, what's the doubt in this?
Sir, I couldn't solve this.
So is that recursive one?
Right. Uh, okay. Did you sort of like try copying the code into the interpret the source code file and try executing
No,
it?
sir. I
Click
didn't
on.
try.
Sorry.
Sir,
I didn't try to execute it.
Okay.
sir, I solved this. Can I tell vaguely?
Yeah, sure.
So F5578. So we just putting that n value to that 15578 to that first. It's going to the first invoking condition. So G55780. So it's coming to this next below function G5578A. So A is okay. So A is 0. So you going to that card. When n is 0, it will return A. Otherwise, you coming to that otherwise condition. So G. Um, okay, so they are given like what is Q and what is R. So Q is nothing but it is a floor division of n and n10, and R is nothing but it's a remainder, and Q is quotient. So if you computed that recursively, you will get that. You finally coming to that n is equal to 0 condition, and you will get an A to that one.
So when we go to the otherwise, what will be the value of O?
The Q is nothing but div n10. That means
Yeah, I
5.
know that. I'm asking about A.
Oh, A is 0, right? Because you are coming to that first condition, G5578 and 0.
Right, right.
So the A will be automatically 0.
Okay, okay, yeah. Yes, sir, I got it. Thank you.
Right. A is 0 always, right? Because that execution G and 0.
Yes, sir.
Yes, sir.
Right. Okay. Cool. So in that case, let's wrap up the session then. Thanks for attending the live session, and thanks for making it interesting. Looking forward to the next session coming Friday 6 to 8. The same meeting link. Thank you all.
Thank you so much, sir.
Thank you, sir.
Thank you.
Lot more informative section. Thank you, sir.
Thank you.